Okay, great. And I see the numbers are climbing, so I think we can get started. So welcome to our second phase of this workshop series, where we're going to provide a little bit more detail on the actual PyPSA-RSA model that we've been working on. I think what you'll find is that the level of detail and information is going to be a little bit of a step up compared to what we presented last week. And it's quite a lot of detail to get through in a kind of 2.5 hour session. But the aim is for us to have this as a recording and as kind of a resource bank that as you go through and work through the PyPSA-RSA model over time, that you can refer back to it. And we will have a platform on Discord where you can ask any questions if you're struggling on getting going. So just in terms of the workshop last week, you will be able to find the slides. They are now uploaded to our website. So if you go to publications, and then you can see the slides and the videos that are available here. And we will upload today's workshop as well to the website. Let's put this back in presenter mode. Okay, great. So in terms of the sort of scope of work for today, we're going to be looking at just a quick recap of what does the PyPSA-RSA model actually entail, and how is the model structured. I'm going to then take you through a little bit of the workflow and how you can approach going, essentially setting up the model and how you would run that in Python and using the snake-make workflow. I'll then sort of take you through some scenario spreadsheets and basically how you set up a scenario, how you input that data, how you come up with different combinations of input assumptions, and then how you can run that through the model. Finally, we'll also look at a bit of post-processing, so how you can start to make some nice looking charts. And finally, the kind of where the model is heading to and some of the multinodal analysis that we've been working on. So again, as usual, I think we'll pause for questions as we go through. So please, if you have any burning questions, put your hand up and Indivor will let me know. So jumping back into what does the PyPSA-RSA model actually entail? So essentially what it is it's just a series of actually a very limited number of Python scripts. And you'll see once you've synced the repository on GitHub, there's a folder called scripts. And there's only really a few limited Python scripts in here. There's something called helpers, add electricity, base network, build topology, a file for if you want to do any custom constraints, and the scripts to prepare and solve the network. So what we covered last week was looking at the pre-processing and input data, and that specifically would give us our resource file. But really the main workflow that happens in PyPSA-RSA sits in what we would call our snake-make workflow. And we're going to get into a little bit more detail of what's entailed in that snake-make workflow and how it works. But basically, it's an automated workflow management tool that allows you to run through all the scripts in order and find what data is missing, and then automatically run the scripts that need to generate the input data for the next file that needs to be solved. All right, let me just go back. Then in terms of how you actually set up scenarios and then run those scenarios, so you can think of this as kind of the fixed code base, and then you've got all your different scenario input assumptions. And we've chosen to do that specifically in an Excel-based format, mainly because it was easier to share across the business for people that aren't working so much in Python. That anyone can really quickly look in an Excel file and then see how the different input assumptions are changing over time. So we have those as a series of what we would call scenario workbooks. And everywhere where you see there's a green block here, that's a different definition of input assumptions. So we have one overall scenario, and that consists of different sub-scenarios, and those all feed input information into the different scripts that then help you generate the network file and then solve it. So just getting into then the actual workflow and kind of how that works out. So SnakeMake is, as I said, I think it was developed in the bioinformatics space, but essentially it's a library that helps if you have complex data flows, lots of dependencies on different scripts, and then understanding which scripts need to be run for other scripts to be run. And really what it allows you to do is to just pass it a command and say, for example, I want you to generate a solved network file. And what it will do is then automatically determine the best way and the best order of scripts that need to be run in order to generate that network file. So for example, if we started off and we gave SnakeMake and we said we want to get a solved network file and we haven't run any of the other scripts before, what will happen is that it will say, okay, it needs certain input files in order to generate the solved network file. It will check if those exist, and if anything has changed since we last ran it, it'll say, okay, well, we need some files that are then the output of this script, so then it knows that it has to run this script, and so forth. So it works its way back to the beginning. You can also then tell it at any point in the workflow, let's say you're just interested in one of the intermediate outputs, you can just tell SnakeMake just to build that output, and it will only run the scripts if it sees that something has changed, either on the input data or if the script itself has changed. So when we look at the SnakeMake workflow, essentially we have these different scripts, and those scripts sit in something called the SnakeMake rule. So a rule just says it takes certain input data and it generates an output, and it uses a Python script. And I'll explain a bit more what that looks like later on. So essentially, we have these different rules which correspond to Python scripts within the code. And the first rule that we run is something called build topology. So for single node copper plate models, this doesn't really make too much, it doesn't have too much of an impact because it's a single node. But when we start to look at the multi-nodal analysis, essentially what this does is we give it different supply regions. So we've got GIS data. We also have GIS data for what the transmission network will look like and how that might change over time with the TDP, and also some GIS data around population and GVA distributions. What we do is we take that and we feed it into this build topology network. And essentially what it does is try to estimate what the inter-region transfer capacity is between different buses. And we'll go through at kind of the end of this presentation a bit more of a detailed workflow of how we do that and some sample calculations around those line transfer capacity calculations. Then that essentially, now we have, we don't have a PyPSA network or anything. We just have information that says, for example, if we're doing our 10-node network, the Western Cape is connected to hydrocluster, and there's so many megawatts of transfer capacity between those two regions. Now that we know kind of the lines and buses, the next step is to actually then build basically a kind of wireframe PyPSA network. So we don't have any generators or storage yet, but we start to add in some of the simulation configuration settings. So for example, how many time steps, or basically how many simulation periods you want to run. And then there's also some configuration settings. And that now we've got a PyPSA network. It's got snapshots. We've added the buses and some information about the buses. And we've also added the lines between the buses. The next step is kind of one of the more involved scripts within the model. And this is really about now how do we populate the network with all the information about different generators and storage technologies. So there's quite a lot of information that goes into this, but essentially we take existing generators and storage, we look at their GPS coordinates, find out where they are, attach them to the closest bus, and then providing all the kind of performance data for those different plants. So it could be technical, so kind of installed capacity, ramp rates, fuel consumption, all of that. And then for renewable generators, we also look at where they're located. And if you remember in our session last week, we generated renewable resource profiles for all of those existing sites. So we take that information. We also then look at new generators and if we wanted to expand the network. So that's where the extendable generators and storage comes in. And essentially then all of that information goes into the network. And now we have a network that has generators and storage. We've got our snapshots, our lines, our buses. And we're now almost at the point where we're ready to solve this network. Finally, then we want to do some final preparation of the network before looking at solving it. And this really involves mostly adding different constraints into the model. So we'll work through this in a bit of detail, but essentially we leverage the LinoPy backend in order to create different constraints in the model. There are also some built-in generic PyPSA functions that we can use in terms of global build constraints, for example, across different carriers. We also add some operational limits, and we did quite a bit of work to have a sort of generic way that we can input operational constraints into the model, and then also some constraints around planning reserved margin. So now finally, we've got our kind of fully populated network. It's got all the components in it. And now we pass it to the solver. Again, in order to solve the sort of decent sized models, we probably are going to have to rely on a commercial solver at this point. And you're welcome to reach out to us. We can kind of share our experience, but we currently use Express. There are some different options coming into the market. For example, COpt, MindOpt, and then there's the kind of traditional Gurobi, Cplex, and Express as different options. If you're part of an academic institution or you're a student, I believe you can get an academic license of Gurobi, which is kind of the leading solver, I'd say, for free. Finally, once we've solved, we've kind of prepared the network, we've solved it, that now is the kind of capacity expansion network. Because we solve our model in full chronology, we haven't done a lot of unit commitment dispatch work after that, but it's definitely a script that we are busy working on, where now that you've solved for capacities in capacity expansion mode, now you do a bit more of a detailed unit commitment dispatch. So you take the capacities that you've optimized, you now fix those capacities, and you can either do a mixed integer, so it's sort of a full unit commitment dispatch. But another useful function that PyPSA has is a linearized unit commitment. So instead of, for example, if you have a generator that's on or off represented by 0 or 1, instead it can vary anywhere between 0 and 1. And we actually find that linearized commitment is quite useful if we're not modeling at a unit level. So, for example, if you have a station and you might have anywhere between 0 and 6 units operational, by being able to vary between 0 and 1, you get a kind of reasonable representation. And because it's linear, then it's a lot less computationally intensive. So I don't know if anyone has any questions kind of on this like very basic workflow, and then if not, I'll jump into just providing a bit of information on what actual snake make looks like. How big the problem needs to be, okay, before you have to invest in a commercial solver. It's a little bit of trial and error, I'd say. And kind of the only way to know for sure is to kind of test it. So I'd say really if you download Highs or CBC, you can essentially set up a model, and then you can basically try to solve it. And you'll find quite quickly, especially if you're looking at if it's printing out the convergence criteria, if, for example, it's been running for 2 or 3 hours and it's only done like a couple of steps in convergence, that it's unlikely to solve kind of within 24 hours or more. But there are some techniques that you can apply to make the problems more tractable for an open source solver. So the first is to try and look at different time sampling. So instead of solving 8,760 hours within a year, you look at either doing the segmentation approach, which I'll talk a bit about later, or you can start to kind of work with the TSAM library yourself to do some more representative weeks. That can reduce the size of your problem significantly, and then you can solve it with an open source solver. The second is just, I'd say, when you're doing perfect foresight capacity expansion planning, the models are very big. So what you can do is rather do a limited number of years that you want to solve, or even you can get quite a lot of information out of a single year, for example. And then that makes it a lot more kind of streamlined and tractable, and you can probably solve a model of that size kind of within an hour or two. So there are some specific solver settings, which I'll explain a little bit later on. So there's different algorithms basically for solving linear programs, and what you want to do is make sure that you're using what's called an interior point solver, and you want something called crossover to be switched off. So I might as well get into now. The main kind of algorithms that you have are kind of simplex or dual simplex. And then there's a kind of more approximation method, which is the interior point method. And really for the size of problems that we're looking at, you can really only solve with the interior method. That gives kind of the best performance, and it gives a very good approximation of the final outcome. Okay, so basically, I think just to start off with, what does a snake make? Like, what does the workflow actually look like? And what does a typical rule look like? So within your workflow, there are two very important files. So the first is called a snake file. And the snake file is basically a kind of, it contains all your snake-make rules. And it's what snake-make uses to essentially run through the workflow. Second important file that you need is a configuration file. And that's saved as a YAML file, which is a kind of text-based input. And that sets up a lot of the configuration info that you might need. So in terms of kind of what a what you'll see when you look in our snake file, and we'll jump across to that in a second. But you first have the definition of the rule. So in this case, we have the rule build topology, and then you have kind of your inputs. So these would be input files that SnakeMake will use in the workflow. And then you have the outputs that you want to run. So for example, this rule here is going to take GIS data for supply regions, existing transmission lines, planned transmission lines, and GDP and population data. And it is going to produce two GeoJSON files, which are kind of a GIS type format that has the buses and lines. So we now have within our Python script, when you're running in SnakeMake, you get a SnakeMake object, and essentially you have access to different inputs and outputs within your Python code. So for example, if you have a line that says, I want to read in the supply regions into a GeoPandas data frame, you can then within your Python script go GeoPandas, and you can read that file, and you can go snakemake.input.supply regions, and it will then automatically provide you with this input string that you need. Then there are some other parameters that you can specify. So for example, threads, here it will only run this on a single thread. This can be important if you're running multiple snake file. If you're running a single snake file, but you're wanting to run multiple things in parallel. Sometimes you want to watch that. You can also set the maximum RAM that's suitable, etc. And then finally, importantly, you need to tell it what Python scripts it needs to run. So our rule build topology, and it's going to run the Python script called build topology.py. The final kind of important concept within SnakeMake is something called a wildcard. And wildcards are essentially things that you would vary if you want different files to be generated. So for example, wherever you see these kind of curly brackets and something in between, that's something called a wildcard. So when you want to run a different scenario, you would change that wildcard. So if you had a whole, whichever specific file you would want, you would then vary that scenario. What happens when you have multiple rules is that wildcard becomes very important, because another rule might use this file as an input to it. So it tells SnakeMake that it has to go back along the chain, and it has to find, okay, which is the rule that it can use to make that specific scenario's file. And then it first runs that script. Now it knows it's got that file, and then it passes it to the next kind of rule in the chain. So I'll hop across to just give you a little bit of example how that works now. But essentially, this is an example of how you would run the SnakeMake workflow within the terminal of your Python, in your Python terminal. So let's just jump across. Okay. So at the moment, I'm in the scripts directory, but I just want to show you where the snake file. So one folder structure up from scripts, you'll see there's something called snake file, and there's the config.yaml. The two files that we need, I've already got them open. And essentially, this is what it looks like. We've got all the different rules. So right from kind of build topology, base network, add electricity, prepare and solve the network, and then finally the network dispatch file. What we do is we've kind of got a little bit of a hybrid process. So we define all our scenarios in Excel, and then we've got a flag that says run that scenario or not. So what happens in the snake file is ahead of time, it sees, okay, which are all the scenarios that we've put that flag that we want it to run, and then it will automatically run through all of those, and it will work out which of those scenarios it can do in parallel. Obviously, depending on your solver license, you can typically only solve at one kind of network at a time, but you can do a lot of the building of intermediate data in parallel. So if you have 10 different scenarios that you want to run, it will run all the scripts that up until the solve network, it'll run in parallel. And that's very efficient. And then basically the bottleneck then comes on the solver side where you can only run one at a time. So if we were to call this workflow, what you want to do is make sure that you're in the main PyPSA repository. So for example, just trying to let's just do if I try to run the snakemake workflow from within another folder, you can see that it says basically there's no snake file found. So you need to run it from the same folder that your snake file is. And here's an example of basically a snakemake command. So we're going to say snakemake. This -J1 is just basically telling it to use one core. And then we have the name of the file that we wanted to generate. So if you remember back here, we have an output file, and we have, for example, lines and buses, and here we have something called a wildcard. And the wildcard is just a name of a scenario that we want to run. The flag -F just means it's going to force it to rerun that. If those files already exist, then it's going to tell us that there's nothing to run. So for example, if I try to run it now, it's going to tell us that basically all the files are up to date. There's no need to run this, but I'm going to force it to run so you can see as an example. So I told it I want this file, and you can see what it's done is it said, okay, well, it knows that I need to run the rule build topology in order to generate that output file. And now it's going to automatically generate that file. And we'll see, I think it's saved under resources. Look at just modified. Here we have there we go. It's just run those two files. And if you wanted to have a look at what those look like, you can just open QGIS quick. So QGIS is basically just a great open source way to view GIS data. So we can add a vector. We can go find our file now. So it's resources. Okay, so we've been running it in single node mode, and we can see that because we've run it in single node, there's only one region. And we've got our GVA and population data by a single SIG code. But obviously, if we ran this in 10 node mode, then we would see 10 different regions there, for example. Close that. Okay, so that's if we wanted to run a single file within the workflow. But let's say that we actually just want to run our entire workflow. So what you'd have is is this specific command, and we do provide it in the README text file, but it basically just says solve all scenarios, and that's going to look into the Excel file, and it's going to say, okay, these are all the scenarios that we've said you must run, and it's going to then sequentially run through all of them. So you can see now, because I'm running a full scenario, it's now going to run base network, build topology, add electricity, prepare and solve network, and then finally it's going to say that it's solved all scenarios. So you can see the workflow is now basically starting at the beginning. So it's now solving that topology. It's now moved on. So it's generated our kind of initial base network file. Now it's moving on to the add electricity script, and it's busy kind of adding all the different generators, etc., to the model. And once it's done that, it will then solve the network. Okay. Etienne, I see your question on pumped storage, so we'll definitely have a we'll get to that configuration in a second. Bruno, I'm not sure. So I see you've got a command snakemake not recognized. Yeah, so snakemake is a package within Python that has to be installed. A word of caution, if you're trying to run snakemake from directly within Windows, I have heard that there can be quite a few issues in getting snakemake to actually work. You don't 100% have to use snakemake. I'll show you how you can run some of the scripts more manually. But typically snakemake doesn't seem to play so well with Windows. So it's best to, if you are using a Windows machine, to run it under WSL, and then it should be a lot smoother. But can help you out if you get stuck. But yeah, it is a package that should have been installed as part of the PyPSA-RSA installation script. Yeah, so you can see I'm running it directly from my Python prompter. Okay, so essentially what we have is we've run through the network. So you can see these are all the steps that it's taken. So it's attached load, fixed generators, extendable generators, storage. It's doing some kind of additional work, basically around profiles, fuel prices, checking for anything that could be an infeasibility, adding load shedding, and now it's exported that network. So the next step is now it's onto the prepare and solve network. So now it's taking this fully populated network, it's applying any constraints, and you'll see it'll start to write to the solver soon. Essentially, it's going to write that .lp file, and then that gets passed to the solver. So while we're going on, I'll just let this continue to run so you get a feel for kind of how long a typical, so this is a single node scenario, but it's kind of solving in every 2 years, so it is quite a big file, and that would typically take about an hour to solve completely. Okay. So this is just coming back to basically how we, and I must say this kind of Excel-based interface is a kind of a bit of a hybrid between how some of the other international PyPSA models work and just how we found setting up scenarios and running them works best for us internally. So that part of the script where it says basically run all, you can see that I'll show you in our scenario setup. We can basically have rows with all the different scenarios. And then if you give it a flag for if you wanted to run that scenario or not, and then it will automatically. So for example, you can leave it overnight and SnakeMake will run through all of the different scenarios that you've defined and that you want to run. So we can pause. I don't know if there's any other questions there. If that makes sense to everyone. SnakeMake itself does have some basic examples. So if you go into there, read the docs, they've got some examples that tell you basically all the different commands and how you can use SnakeMake itself. There are also one or two tutorials. I think the Fabian Neumann tutorial on PyPSA Europe essentially also walks through how they use SnakeMake. And they really rely on SnakeMake for the entire workflow, so they don't have this kind of Excel interface. So as I say, the Excel interface is just what we found works best for us. And interested to get everyone's feedback if it's something that works for you, or if going back to just a full SnakeMake is kind of a better approach. Okay, so essentially what we have is, if you look within the folder structure, you'll see something called scenarios. And if you click on scenarios, we're going to work from this folder that says MERP 2024. Now there's always kind of basically what I call the global scenario definition. And that's this folder that says, or this Excel file that says scenarios to run. So if you open that up, what you'll always see is that we use kind of to help us filter. So the kind of scenario definition is always the kind of first on the left-hand side. And then if you want to filter, I'll show you in some of the other Excel files that helps. So this is kind of your global control over scenarios, and it tells you which of each specific sub-scenario you want to use. So for example, you might have different assumptions in terms of how the coal fleet decommissions. So you might have, under your base assumption, coal fleet decommissioning happens over a certain time, and then you might have some net zero assumptions where you have accelerated decommissioning schedule. So essentially, each one of these columns refers to different ways that you can assemble different sub-scenarios. So under fixed conventional, you might have, in this case, we had kind of 3 or 4 different definitions in terms of how the existing fleet behaves. And then each one of our main scenarios that we run references different combinations of all these sub-scenarios. So essentially, I'll get to this first bit here, but essentially we have fixed. So these are essentially scenarios that are related to any existing generation. Then we have a set of definitions that are related to any extendable generators. So new investments that you want to make. So we've got active, we've got parameters, which is mostly linked to cost and performance, and we've got build limits. So basically how much your min and max installed capacity is for this. Then there is also extendable total max. I think I was playing around with this earlier and I accidentally copied over it. Then we also have important definitions around operational limits. So I'll get into that. Outage profiles, annual availability. So that's mostly for conventional generators. And then finally, some kind of global assumptions. So you have CO2 constraints. I'll explain what min station RLI is. You've got your load trajectory, reserve margin, and capacity credits. So the final kind of set of inputs you have are basically which numbers of years you want to run, how many, if you want to use a single node model or multi-node model, for your renewable resources, which areas you want to use, and this must link to how you define them when you ran the pre-processing script for the renewables. Line expansion, these two flags we're currently not using. And then your multi-node model, basically you can then say what different grid expansion pathways do you want. So this would say existing grid plus TDP. And we also have an option to add in manual additional lines. So user-defined lines that would compile those three, but this is only relevant if you're running more than a single node. No, yeah. So we obviously kind of you could generate like different combinations of all these scenarios automatically using Python, Gregory. But basically, we set them up manually at the moment. So we sit down in our kind of workflows. We want to define a scenario. What are all the things that we want to test? And then we would have our sub scenarios and assemble it manually. It doesn't take very long. If you want to run like thousands and thousands of scenarios, then you might want to do it automatically in Python. But you probably wouldn't be able to solve that many large scenarios anyway. Okay, I actually want to just open from here. Okay, so sub scenarios, essentially, these are now like the nuts and bolts, the actual information. So the first to start off with is fixed. So remember, fixed is kind of the Python, the PyPSA definition of anything that's already existing. So you've got your sub-scenario definition down the left-hand side, and you'll see that, again, that corresponds to something that you've defined over here under fixed conventional. So we've now, under the fixed technologies spreadsheet, we can filter. We've got then all the existing generators and some parameters about them. So ranging from installed capacity, just hide this. So yeah, unit size, installed capacity, and really from a conventional generator point of view, what we vary the most is decommissioning dates, heat rate, emissions, fuel prices. Some of these parameters will only get pulled in if you are doing the unit commitment dispatch. So for example, min stable levels, min up and down time, max ramp startup and shutdown. These are all only get used in unit commitments as well as startup and shutdown costs. So at the moment, we're not using these extensively within the model, but most of the other parameters are. You'll see when you open the spreadsheet that there's a definition of generators that has a star or a double star. So this is kind of a workaround that we've implemented. So we don't do unit level modeling. So for example, you might have one station and it's got 6 individual units. If you wanted to, you could model all 6 units, but it obviously increases your computational cost quite a lot. But basically what we do at the moment is split the power station into 2 kind of sets of units. So you might have, you can see here for Arno, we've got 3 units, and then the double star is just the second definition. So that's how we split it down the middle. So we've got 3 units and 3 units, and then we can decommission those at different times. So it's not the kind of at a station level, it's not the same resolution as if you would decommission a unit a year. But what we do is we move around the decommissioning dates overall, that we kind of track the decommissioning profile quite closely. So that's just, you'll see a star, double star, that's related to the splitting of power stations into 2 halves. So this is the conventional generators. Then we also have a renewables tab. So again, the definition that you see on the left-hand side then corresponds to these definitions here that you've chosen in your master scenario spreadsheet. And this is mainly anything existing related to existing REAP or projects that we know about that might be coming in the REAP. So essentially, basically, you've got this uh, all the definitions here for your bid windows. You've got some information about these different projects, but a lot of this information has already been pre-populated when we did the resource profile modeling. So at the moment, really what it's pulling from here is some of the costs and install capacity. But the other scripts that we've already ran last week happens to then allow you to work with that. Then finally, we've got storage. So here, different assumptions on pumped hydro storage, as well as then existing battery projects that we know are coming online. Bruno, yes, the question around min stable level. So as I say, we're not running unit commitments in the current workflow. So those columns aren't used. But when we do run unit commitment, we are typically using the linearized unit commitment, which kind of sidesteps this problem of basically you can only have 3 units on or 3 units off, that you can shut down a portion of units within that. So that's the one way to kind of sidestep that. Yeah, modeling with variable O&M. Yeah, so we'll get into that in the code. So for existing PPAs, they are modeled with a variable O&M charge. And then what we do is we have it's a forced take or pay. So I think we say that the model has to use 98% of the available generation. So basically, it can't just ramp these down because these early projects were more expensive. We force them to basically the model to buy all of the energy at this price. I think the reason that we went with 98% instead of forcing all the energy is just that occasionally there might be some solver issues on that constraint if you force 100% of the build profile. So if we come back to just this model that's running through the workflow, you can see what's happened is it's generated the constraints file, it's written that to the file, and now you can see it's sent it to express our solver, and now this is actually running in the background. You can see it's basically converged when these two numbers are equivalent to each other. Okay, so this is kind of the first tab on fixed renewables. Then anything related to extendable technologies. And these are basically technologies that you want to, sorry, for some reason my open office just crashed. Let's try this again. Oh, live demo is always fun, aren't they? And crash. Oh, sorry, I have no idea why my LibreOffice is now doesn't like me clicking on the active tab, so I'm afraid we're gonna have to stay away from that one for now. Okay, scenarios run. Okay, so we basically covered, so fixed conventional, fixed renewables, fixed storage are basically in the fixed technologies tab. Then anything that's related to extendable generators, so generators where we are optimizing the capacity, that is all then sitting in the extendable technologies spreadsheet. So it's a pity that I can't. Okay, now it's not crashing. Great. So what we have is, and unfortunately, the workflow gets a little bit complicated here around the extendable technologies, and I'll explain why. But basically, you have lots of different cost profiles, and then sometimes you want a combination of different cost profiles. So you might want to test what happens if solar PV and batteries get really cheap, but wind gets really expensive or something. So you might not always want all your low costs, all your medium costs, all your high costs together for each technology. You want to mix and match them. So there's a bit of a mapping process that happens within the spreadsheet, which is a little bit of it's a little bit complicated, a bit of a hack, but hopefully you can figure out how it works. The first thing is just this active tab is kind of an override that we use. So basically, if you have some scenarios that are almost identical in terms of all the parameters that you set up, but for example, you don't want one specific kind of generator, you can just basically turn that generator off. And what that will do is it'll just kick it out of the optimization mix. So for example, we had some specific generators that we were doing fuel switching from gas to hydrogen. And if you didn't want those in your scenario, you could switch them off. The next tab, and I'm going to skip the mapping for now, but parameters is basically where all your input assumption data is going. So you might have different assumptions here, like a base case, and typically we have default values as well. So everything from emissions, heat rates, efficiency, ramp limits, lifetime, any technical information that you need to run the generator is basically stored in this parameters. And often you'll have default parameters for a lot of generators, and then you might have more specific, like you might want to keep all parameters roughly the same, but you might want to vary investment cost, for example. And then you can have different definitions of how those costs. So if you want, for example, here are some base investment costs that we might make over time. So parameter mapping is kind of where this hits the road. So as I said, you might want different combinations of how you combine your costs. So let's just actually do two of these. So what this does is it just says, okay, for our high scenario, and this is now what gets referenced in your master spreadsheet. High means that we wanted to use the Meridian high investment costs, and we wanted to use the default costs for everything else. Similar for base. Base is basically the same, but we wanted to use base for some of our investment costs, and some of them we wanted to use the default values that were in the RP. If you wanted to come up with a new kind of combination of these, so for example, if you wanted to test, let's actually just do that. You wanted to test like more moderate PV costs with high battery costs, then that's where you can mix and match, and you can mix and match any of these parameters as long as the parameter in any of these columns has been defined in this parameters sheet. So you can see we have default, we've got ME base, ME high, ME low, and so forth. So those are all You have to make sure that you define all those parameters, and then you can use them over here at any point. So this, again, this scenario here is what gets referenced in your master spreadsheet when you say extendable parameters. So we say here's base, high, RP23. And if you go here, you'll see that we have high, base, and we've defined a scenario called RP23. And that's how that mapping happens. Okay, then in terms of installed capacity, basically we have different build limits now. So there's two ways to apply build limits. So the first is build limits on total active installed capacity, and the second is then annual build limits that you might want to apply. So for example, we have a whole lot of different scenarios here. So just in terms of how the spreadsheet is defined, if you want it to be unconstrained, for maximum build, you just write UNC and the model will automatically pick that up and take that as unconstrained. If you don't want to build anything, so you're forcing that you can't build any CSP here until this first year, you can put 0 in there or any other number. One thing that's important, and it's something that we might change to make it a bit more robust for other people using the model, not us in the future, is that you have to, so any technology that isn't here in your maximum build limit will get excluded from the model. So if you don't define the technology here in your maximum, and it's only for maximum total installed, basically it won't solve that in the model, but it will flag when it reads out that, hey, you've said you wanted to use this technology, but you haven't provided a maximum total installed for that, and it's therefore ignored that. So just don't get caught out by that. We're probably going to make some kind of a check beforehand that it will flag all these things and stop the workflow if any of these things are missing. Okay, so that is then the kind of extendable how you would define these. And it looks a lot when you show it all at once, but obviously I think just the idea is always that these are set up that you can filter them, and then you have a very easy view of basically different constraints that you might want to apply in the model. And then you would change this depending on kind of different scenarios that you're modeling. Okay, some questions. Carrier. Yeah. So essentially, we kind of use a slightly modified definition of carrier. So carrier in the true sense in PyPSA world is really referring to the primary energy carrier. So kind of solar PV, wind, gas, diesel, etc. What we initially did is obviously you will have different types of solar PV generators. So you might have rooftop. I'll explain what R_low is a little bit later. So we've kind of snuck it in there in the carrier term. I think there is a parameter now called type within kind of your n-dot generator. So we might change this in the future that you would have carrier being purely the primary energy carrier, and then type being if it's rooftop and so forth. But ultimately, this is kind of like a key for that technology. Gregory, is utility PV by default always single axis tracking? No. If we go back to the, let's see if I can do it here. if we go back to the pre-processing scripts, it depends how you've set it up. So actually, don't want to mess up my demo. So sec. So in the pre-processing scripts that we had, you have different generators that you can choose from. So it can be fixed tilt, single axis tracking, and we have three essentially. We have kind of a rooftop, a ground mounted fixed tilt, and a utility scale. And this prepare resource profile, you can select kind of which one that you apply. So this is only relevant for new build. And you can, in theory, if you wanted to have different new build, some be single axis tracking, some be fixed tilt, you could definitely do that if you wanted. But basically, only existing plants we use fixed tilt for. So if it is a fixed tilt plant, and if it is a single axis tracking plant, then we use single axis tracking. But any new build, we are assuming for utility PV that it's single axis tracking. Bruno, yeah. So definitely the existing reef, you could model it with a fixed O&M charge as well. I mean that using the capacity factor, and you could get kind of an annualized cost, and that would be equivalent of take and pay as well. This is only really relevant for the existing REAP rounds, so it is relatively, the capacity is small. So whether it's 100% on take or pay, or forcing that bottom 98%, or letting the model curtail it as much as it wants, I don't think there would be a huge difference in the results. But yeah, you could definitely set it up as fixed O&M as well. Are there any other questions on these two spreadsheets? Because these are kind of a lot of the meat of the kind of how you set up the model. As I say, we've been using this model only really internally, and so we could definitely do some more work in the future, I think, about making it a bit more robust for someone outside of Meridian to use. But I think the only way that we can kind of tackle that and see some problems when people are trying to run and install different scenarios is for you guys to play around with the model and then feedback some of those changes to us, but also tackle making those changes yourselves. And we'd be quite happy to review any pull requests that you feel might be a bit more of a smoother workflow. Okay, so now if we go back to our main spreadsheet, we've kind of covered the fixed technologies, the extendable technologies. So the next one.
Peter, just wait before you go on to the next section. Where do you put your metadata? So you have a lot of numbers in those tables, but like, what is the source of them, and how do you document that?
Yeah, so there is a column. Let's see. So most of these do have a column that says, well, some of them are probably not as well documented as others. But we do have, let's say, on the extendable technologies, for example, there is a kind of source. I mean, basically, most of our source is RP, for example. And so we do provide like these are mainly notes for us as we're going along with it. But yeah, if anything isn't clear, we can kind of put a bit more detail in there about references for the cost.
Yeah, so existing coal fleet has a lot of parameters that are not in the RRP, so I'm curious to where you got those.
Yeah, a lot. Basically, the kind of history is that a lot of those came from the existing PyPSA-ZA model. So we haven't touched some of those parameters. The only parameters that we really vary are the kind of decommissioning date. In terms of where the kind of history of the original PyPSA ZA model is, I believe it came from work that Jan Kalitz was doing with Jonas Hirsch at the time. So uh, aligned with some of the initial CSRR Plexus model.
Okay.
But yeah, so Summer, I don't know if Joanne's here on the call or not. If she is, she can also jump in. But a lot of it is either kind of from publicly available data sources, what CSR put together at the time, or just things like ESCOM, like generic information that's available, or some estimations. But it would definitely be great to get some feedback like from other models. I mean, we're putting all this data out there, so it would be great to see if how those numbers line up compared to, for example, what's in Saturn.
Sure.
Okay. So okay, so then we've kind of covered then those existing generators. The next kind of important tab is around operational limits. So you'll see that there's a spreadsheet called operational constraints. And this is just around basically how you can force specific behavior for different generators within the model. Um, and this was actually quite a headache to get right in the end to make it generic. So it might not be fully robust, but hopefully we can refine it. But basically, what you have is kind of your definition of your carrier, which is typically related to the technology and your fuel source. Uh, and you can use a plus for many of these. So, for example, if you wanted to limit um, the the combined output of wind, solar, and CSP, you can say plus plus plus, and it will automatically then add those together. And we were doing this as a kind of a grid constraint. So you can see that we kept that to about 2035. So we said if you're behind a grid constraint, your combined output of wind, solar PV, and CSP in high resource regions must be below 13 gigs until 2035, where it's basically unconstrained. You can set up a definition based on output power or capacity factor or output energy. So you can basically, for example, here, where's something that makes sense? We forcing, for example, here, a minimum capacity factor of 30% over the course of a year. I'll cover this just now, and we want to apply it to both existing generators and fixed generators. Same thing here. For example, if we wanted different combinations of minimum annual capacity factors, these can all be changed. So if you wanted to make that higher or lower, you can do that. And at the moment, this is based on the full nominal installed capacity of the technology. So, for example, that would be 35% based on the full installed capacity of the plant. But if you, of course, for most of the RP scenarios, the EAF was sort of below 50% for the coal plant. So basically, this is actually closer to saying 70% of the coal fleet that was running as a minimum. But an alternative way of specifying that is that you could say true on include PU, and then it will say only 35% of the maximum allowable generation. So after you've taken into account outages to apply that constraint. Then it can be minimum or maximum, and then also just units. So for example, we had some work around how we did fuel switching. The fuel switching is not very optimized at the moment. We didn't have a lot of time when we were doing this for RP. So the kind of very crude way that we're doing it at the moment is that we have different generators and they fuel switch at different points in time, and the model can pick, does it pick a gas generator that stays gas for the whole period? Does it pick a gas generator that changes to hydrogen after 2040, 2045, etc.? Um, you can then also specify some variations of the period that you apply the constraint to. So for example, if you wanted a minimum monthly offtake, you could do it weekly or for the year. Those are all things that you can do in the model. One thing that you'll probably find if you try to run the model at the moment, we were using a slightly older version of Pandas. So the model might crash because it's using dot week in some of the group by terms, and I think Pandas has changed that now. So we might have to just push an update for the new version of Pandas that uses ISO calendar. But that's a small fix if you want to do some optimization on the week. So you can add in any row here, and you can apply kind of any constraints on power, energy, or capacity factor from hourly right through to annual. And at the moment, it only applies it in kind of year steps. So that's then how you can define specific operational constraints. Then finally, the kind of some information then around outage profiles and kind of availability. So that's here under plant availability. So annual availability is kind of basically like an override. So anything that's defined here underscore EAF at the end, it will take whatever profile that you've said. So if you give it, for example, the existing hourly variation in a coal generator, and if you work out that average EAF over the year and it comes to like 70%, but then you've provided like 30, 39% over here, it will automatically just scale that profile down. So this is kind of like an override that we use to say, okay, this is how the EAF will change over time. And then you might have different EAF, for example, projections. It is possible to provide different EAFs at a station level. At the moment, we have only used a single coal cost and a single fleet EAF. And that's more just around data availability. So we just used what was available or what we could back calculate from what was given for the RP, but there is flexibility to assign availabilities, different availabilities to coal generators separately. In terms of then how the outage profile gets applied, so this is kind of the overall annual EAF. Then the outage profile, there's two types of outages that the model considers, so planned and unplanned outages. And again, we've just kept the same profile for the whole fleet, and this is then based on kind of looking at some of a reference here from I think, can't remember which reference here exactly. It was probably before load shedding. So around, I think it was probably 2019. And what this is just a weekly average outage profile. But we do provide the kind of ability to provide some standard deviation noise around that. So it will set like a very kind of square shaped profile, and then it will add noise to that depending on what you provide here. So we have kind of a planned outage profile that changes across the year, very similar to how Eskom's current planned outages. So planned outages much lower in the middle of the year than, um, sorry, yeah, in winter than kind of in the summer periods. And then at the moment, unplanned outages just there's some variability across different units. For example, you can test those and you can then apply more noise to that. Again, just because it says 0 here, this is just basically coming up with the profile. The annual availability is what sets the overall level. So for example, we just, if this is all zeros or if it's all the same number, essentially that just means it's a flat profile. And then we take um, so for example, you might have Kuberg specified as 90% availability flat. So it would be a flat profile from the weekly averages, and then this overwrites it, and you get a 90% profile. Uh, Obviously, for example, if you take something like Kuberg that has like an 18-month refueling cycle, you get quite a lot of variations around just a flat profile. But for the capacity expansion planning, especially once we go into like 5-year steps, it because you're not solving every year, you can get a bit of anomalies where if it's a year that Kuberg is on maintenance or not on maintenance, it can make a big change to the results. So that's why for the capacity expansion model, we just assume a flat profile on that. Minimum station hourly capacity factors. So this is basically just an override that we use to, in the capacity expansion model, you're not doing a full unit commitment. So you basically, if you let the model do what it wants, as long as it's staying within ramping rates, it might ramp down the call to completely 0 in the middle of the day and then ramp it up in the evening, which is something that wouldn't necessarily be realistic. So what this is just kind of for the capacity expansion model, it's like a floor that we set. So basically, any generator in the fleet, and remember we're talking multiple units combined, basically we don't let that ever go below, say, 30%. Once you get to a more detailed unit commitment, then obviously you can get to min stable level, and whether unit switches off or not, that's a bit more detailed. But it's not possible to do both capacity expansion and unit commitment in the same model, because as part of the maths, you have a status variable that gets multiplied by an installed capacity variable. So both of those can't be unknowns in terms of keeping the model linear. So that's why typically you have to solve your long-term capacity expansion plan and then do a more detailed dispatch afterwards. But this is kind of a number that we've been tweaking to try get basically some realistic understanding of how much capacity is going to be used from a coal fleet, for example, in the capacity model and how that aligns with the dispatch model. Okay, then so that's the kind of annual availability. Then we've got some info around CO2 constraints. It is possible to give it a full carbon budget for the period, but because we are typically not solving every year in the capacity expansion model, you land up with these very kind of step down changes, which is quite difficult to get your overall carbon budget right. So what we've mostly been doing is applying an annual kind of decreasing carbon budget for each year instead of an overall defined. And you can find that under carbon constraints. So anything related to carbon, you can see we have some different parameters here. And then we also have some fuel intensity values. And these do include upstream leakage on gas, for example. And then, yeah, carbon tax as well, if that gets applied in the model or not. Final, then we've got different load trajectories, and then planning reserve margin. So planning reserve margin and capacity credits kind of go together. And this is just basically if a planning reserve margin is active, so for example, when we're modeling some scenarios for RP where initially that constraint is violated and you're not building enough new capacity to basically hold that constraint. You want to turn this constraint off to avoid it being infeasible, and then you might want to switch it on later on. And then what you would set your planning reserve margin at. And then we had some different tests where we were looking at different capacity credits for different types of generators. So those two go together there. Final, and this is kind of a new feature that we're working on, so it's still a bit new in the process. But basically, when we start to do a multi-node analysis, then if you wanted to look at adding in, so you can take the GIS data for the existing ESCOM network, what we've got from the TDP. But let's say you wanted to test, okay, well, what if we built a new 765 kV line between two regions? You can specify it here in terms of the voltage, the length of the line, and how many of those lines you would build when. So it's kind of a manual way if you want to add additional lines into the multinodal model. Planning reserve margin. God, if you give me 1 sec when we get back into the presentation, I'll go through that. So that we're a little bit behind time. It's a bit of a slog to get through all the spreadsheet inputs, but that's kind of what we've been using to set up and run spreadsheets. And we'd really be happy to get any feedback on different numbers and how those compare to what other people have in their models. Okay. So just in terms of kind of, I think a starting point for most people will be based on the single node model. And that's kind of what we've built most of our analysis around the RP. And the question was just how could we deal with some kind of representation of grid constraints within the single node model while we kind of are moving towards the multi-node model. And the way that we tackled that as a starting point was that essentially we defined different types of solar and wind generators within the model. Sorry, God, that one went straight over my head. Okay, so planning reserve margin joke. So basically, solar and wind, we kind of took an aggregate of the kind of provinces with the highest resource profiles, and then we called that like our solar PV generator, and then we had a lower solar PV generator that was in slightly lower resource profiles, regions at least, and that's sort of much more applicable to wind, for example. So we have different costs for wind in these provinces and a slightly different resource profile. And then we have the kind of high wind resource. And essentially what we did was we applied two constraints. The one was up until about 2035, we limited the installed capacity of generators in the high resource region. So, for example, the model can only make investments in low wind resource areas, and then post 25, then we would open that up that you could start to make investments in higher resource areas again. Obviously, once you get to the multi-node model, it's automatically then making investments in different regions, and it has a representation of the grid between it. So that then kind of limits it. You don't have to have these different categories of generators because it's already implicitly handled within the model. Just on planning reserve margin, we found that this actually makes a significant difference to the model outputs. In fact, the model it's one of the parameters that the model is most sensitive to. And historically, the kind of capacity credit approach has always been kind of dispatchable generators getting almost like 100% capacity credit, and then sort of you have some capacity credit for wind, but PV, nothing, and different lengths of battery storage have different capacity credits. Now, I think the applicability of this planning reserve margin approach is something that's I think questionable. This kind of taking your maximum demand in a year and saying that your installed capacity times by your capacity credits has to be X percentage above your maximum demand. As we start to move to having more and more variable renewables in the system and different weather years, I think there's some new approaches to how you would determine what is an adequate system that has some headroom in it. And from what we can see in the literature, it's not so much about this kind of very brute force planning reserve margin, but it's more about now you have to start to run multiple weather years and look at some more statistical parameters around potential loss of load. So for our RP work, we kept it kind of very much along the traditional numbers, so it's comparable with other studies. But for example, applying 100% capacity credit to our coal fleet doesn't make sense in the context. But what you typically see is as the coal fleet initially planning reserve margin isn't an issue because you have this massive coal fleet and it's got a high capacity credit in the kind of typical sense. But as you decommission that coal fleet, you start to build mostly a mix of OCGT and CCGT. Well, actually, for the planning reserve margin, it's mostly OCGT and some battery storage. And depending on the different capacity credits that you give those, the mix between OCGT and storage can change quite a bit in terms of the final projections. Coal decommissioning, at the moment, there's kind of just 3 different scenarios. So there's kind of the planned shutdown, and then we have 2 accelerated decommissioning schedules. So we've got a basically coal off by 2040 and then 2050 net zero. And there isn't endogenous decommissioning available within PyPSA as a functionality yet. So most of these are all exogenously applied. And we kind of reference some of the previous Plexos work that the CSR did for us, which had some endogenous decommissioning of the coal fleet, and we kind of just followed those profiles. But definitely something that we hoping gets added to PyPSA as a functionality soon. In terms of how to model dispatchable generation, specifically combined cycle gas turbines, we've come up with a slightly different approach to how CCGTs are typically represented. So in a lot of other models, the CCGT is really basically represented as a single generator. And it has then quite tight constraints in terms of how that generator can be operated in the power system. And a lot of that really boils down to the flexibility of the steam bottoming cycle. So the heat recovery steam generator and the steam turbine have a lot more stringent ramping constraints on them than the OCGT. But when we spoke to project developers, essentially the CCGT is the exact same OCGT that you would purchase if it was a standalone plant with this bottoming cycle on it. And from what we understand, that you can get an intermediate bypass between them. So, for example, you can run the OCGT part of the CCGT completely in a flexible way. It can ramp exactly like it's a peaking plant, like our existing plants, where you bypass the HRSG. And then when you want the higher efficiency, you can then make use of the waste heat. So what we've decided to do in our current model is that we actually represent CCGT as two separate components. The one is an OCGT, which has no specific constraints around it. And then we have the steam bottoming cycle, where we have sort of some minimum I think it's annual or monthly capacity factor constraints and a bit more stringent ramping constraints. And then the way we link the two is that there's a custom constraint that looks at the output of the OCGT in any hour. And it says that the amount of heat that is being exhausted from that OCGT basically is a function of how much power you can generate in any hour from the steam turbine cycle. So if your OCGT is running at 100% output, essentially then your steam turbine, there's a ratio between, I think we use around 40%. So it's for a 2-on-1 configuration with just over a gig of OCGT and about 460 megawatts of auxiliary steam turbine. This is if we see how that's dispatched in the model, typically what happens is that the CCG, well, the HRSG and steam generator is running at idle during solar hours and then ramping up in the evening periods. And there's still quite a bit of work to be done in understanding if this is a technical way that the HRSGs can be operated, because basically there's a limited number of kind of cold and warm starts that can be done on the HRSG every year. But what we understand is that you can get a duct burner that sits in the kind of flue gas duct between the OCGT and the HRSG, and that you could use that duct burner to basically keep the boiler at temperature, but not necessarily generating a lot of steam, and then it can then ramp up in the evening. And PyPSA has recently come out with a standby cost. So there's a potential to represent that duct burner as a kind of standby cost. If you're not able to basically keep your steam turbine on idle in the middle of the day, I think we would find probably the investments in that would go down in our model, because it's competing with PV energy during the day. Gregory, yeah, would developers be willing to let their plants run like this? Yeah, I suppose it would be a question of contracting and how that would work. But if we would take it from a market perspective, if you look at what's happening on your wholesale energy price, it's depressed completely in the middle of the day as more and more PV comes into the market. So if you're a gas turbine with the CCGT bidding into this market, you are not really going to get dispatched in the middle of the day. So your system dispatch is really going to basically force this kind of dispatch onto you. So I think the main question is from a technical perspective, can this be done? And if so, this is the likely kind of dispatch that I think we would see on a gas fleet. Okay. In terms of then just some post-processing and how we've now run our model, we've got our network file and it's solved. And now we just want to get some nice looking figures. So if we go back to so this isn't currently in the repository, but I'll upload it today. Essentially now you have a file that you've run, you've got your network object and it's solved. And now if you want to post-process and look at it, the first thing we're going to do is load that. A very useful function that you want to use is something called the statistics module, which will automatically calculate the kind of key group parameters for the model. So if it's a large model, it will take a while. But you can see basically you can get optimal capacity, which is your kind of optimized installed capacity. Then let me just show you what the full columns look like. So you can get basically optimal capacity. Don't get confused by installed capacity. In the PyPSA kind of nomenclature, installed capacity is just the capacity of all your fixed generators. And then basically, as those get decommissioned over time, that goes down, but it doesn't include new investments. So the optimal capacity is the one that you want to look at. Then you can get capacity factor. Dispatch is basically the sum of the actual output energy over a year. And you'll see for storage, that number will basically be a negative number due to the round. It's basically summing up all the generation from the storage plus the dispatch of the storage plus the charging of the storage. And obviously with the round trip efficiency, that's a negative number. But if you want the actual energy that was discharged from the storage, you can look at supply. So withdrawal tells you the charging of different storage systems. Supply is then the output generation. A very interesting one to look at is curtailment. And what that does is it looks at that your maximum power output profile that you could generate, called Pmax PU, and it looks at your actual power output that you generated, and it does a delta between the two to calculate curtailment. So that number basically doesn't make any sense for conventional generators. So you'll see like massive numbers possibly for the coal fleet, and that just means that it wasn't running flat out. But it's very useful to look at for your wind and solar. Then you also have your kind of annual system costs. So both for your kind of annualized capital cost plus fixed O&M, and then also your variable costs. So you can get an annualized cost. And then you can also get some information on revenue and market value. And these are related to basically the wholesale energy price. And then it's looking at the dispatch of each generator in every hour to say, okay, based on that marginal price characteristic, what is the kind of revenue potential for each generator class? So if we start with some simple graphs, so I'm only going to show really plotting for the single node model at the moment. We will kind of, once our multi-node model is done, we'll upload some scripts with a bit more detail that shows the kind of more regional breakdown. But there are some nice plotting scripts already in PyPSA Europe and PyPSA Earth that you can look at if you want to do some multi-node plotting. But just kind of a very simple set of scripts to do a capacity expansion over time, just creating an empty data frame, and then basically grouping different types of generators together. So we had this kind of wind and wind low or solar PV rooftop, etc. You might want to group those together just to make the plot a bit cleaner. And then, for example, for this scenario, you can then plot a stacked bar chart of what that capacity looks like over time for different categories of investments. Similar thing on the energy. So you can then look at the basically exactly the same thing here. We calculate the supply from different generators or storage, and then you can put that together and do a kind of stacked bar chart on kind of the energy that was produced from different techs. And then finally, one of the kind of very useful plots that you'd want to do is looking at different system dispatches and kind of what that would look like on an hourly basis. So here's a example for, so you can specify the year that you want to look at and then the period within the year. So if we're saying 2030, you wanted to look at a full month's worth of hourly data, you could then get different dispatch, and you can start to see periods where you have like high wind availability, and then periods where there's low wind availability and much more kind of running of your flexible generation. The way that we do this plot, I'm just going to make it over a week. So we have the kind of stacked plot of generation. And then obviously you will often, if you are charging your storage, you are having more generation than your load, your kind of contracted demand that you're trying to meet. So how we've kind of visualized that is we plot the contracted demand as the kind of solid black line, and that contracted demand then plus storage charging gives you the top line of your different plots. And if you, for example, if that's a bit messy for you, you can then just comment that out, and you can then say, okay, anything above the black line is charging of the storage, and anything below is then, for example, here you're dispatching your storage in peak periods. So these are just some kind of simple plots that you can do. But really everything is available within the PyPSA network, so you can kind of do any kind of plotting or grouping that you'd like. And most of the information that you are going to be after is in the raw. So for example, n.generators, if you wanted to know what the optimal installed capacity of all the technologies would be. Obviously, for fixed generators, it's that doesn't vary. It's based on whatever was specified. But if we wanted like how much was invested in solar PV, for example, in 2030, you can easily pull that out. And then any dynamic properties that you'd want, it's accessed under _T. So that's for now hourly profiles. And P is going to be the kind of actual dispatch profile that you'd want for that specific generator. So if we wanted to go back to our solar generator for 2030, you could then pull that out. If you wanted to, for example, then manipulate that, and you can use any of the pandas now, different functionalities. So you want to know what the hourly profile is, for example, you can easily Sorry, let me just always get caught out by the multi-indexing. So for example, this would be in 2030, what the hourly profile of power generation for that would be. If you wanted the maximum potential, for example, instead of the actual power, you could do that, and that's a normalized value between 0 and 1 for that time. Okay. Don't know, are there any questions on the plotting side of things? We will make this notebook available, so I think it's more just about spending some time and playing through the different plotting. But basically, once you've solved your network, really, then it's no different to any kind of normal pandas and matplotlib type of exploration of data. So it once you've got your solved network, it's not so much like PyPSA. It's more than generic Python tools and program. For our RP work, just one thing that we found useful was to come up with was basically a little bit of a dashboard that could help us combine all the information that we were after of a single scenario into one dashboard. So I know it's a lot to just look at in one go, but we found that it was quite useful then if you have lots of different scenarios and you can kind of quickly flip between them and you can immediately see how the different bars are changing or your different energy mix, dispatch, any of the key parameters that you're after. So we found that kind of a useful way to interrogate the data. In terms of the kind of how the model performs relative to other models, I mean, I think it's always difficult to compare different models to each other because often the input data is slightly different or not everything is available for you to recreate the model. So I think we're a big fan of the idea of getting some standardized test cases together in the open energy modeling space that we make all of the same input data available for different models. And then we can run and benchmark and compare to each other and see how the results stack up. And I think that would definitely help understanding kind of where the similarities are and where some of the key differences are between the models. So we definitely open to kind of working on that. What we did have was some work that CSR did for us. It's quite dated now, it's sort of around 2020. And that was modeling that was done in the CSR Plexus model. And we didn't have the exact model, but we had a fair amount of the input data to run that model. So what we did try to do was recreate that as closely as we could within PyPSA-RSA, and then that just allowed us to compare the two different tools. So the kind of CSR Plexus model at the time, it's not exactly comparing apples and apples. So for example, they solved the model in every year between 2020 and 2050 in perfect foresight. That's obviously quite computationally intensive. So there was quite a bit of time sampling done in the LT plan, but they did a lot more detail on the short-term modeling as well. And there was also in kind of some of those net zero scenarios, Plexus can do endogenous decommissioning. So that was included. But we basically had the resource data, we had most of the input data, and then we tried to kind of put that through our model and see how the two models compare to each other. Again, realizing we don't have kind of absolutely everything to create it line by line. But overall, kind of in terms of installed capacity, a reasonable agreement between the two models. We see that the Plexus model does have a little bit more pumped hydro storage. So our model is typically not investing in pumped hydro storage at the moment, unless we reduce the price quite a bit, then it does make that investment. So a little bit in pumped storage, and that means that there's a little bit more wind and solar in the mix. So you can see that the overall stack is a bit higher than ours. But I mean, overall, I think the trends are pretty consistent. And then kind of the interesting difference that we're currently seeing at the moment is that although we make the same investments in flexible generation, we do see that kind of our gas production. So basically, this is what's running through the OCGT. And that's a combination of pure OCGTs and OCGTs with steam bottoming cycles. But we see that we do have a higher usage of gas than what's in the Plexus model. So I think that's definitely something that's related to some of the operational constraints and how they're imposed. And again, these are our direct results from the capacity expansion model with full chronology, but we still need to do a bit more work around the linearized or full unit commitment to understand some of those implications on gas. But then, yeah, so the overall in the least cost study, there's more energy in the Plexus system because a lot of that is getting cycled through the pump storage. And obviously that has a kind of a 25% losses in terms of round trip efficiency. So basically this energy that gets generated here, a lot of that energy is going toward, so your solar and wind production is going into the storage, and you're losing a fair bit of that as well. But overall, trends relatively consistent. And yeah, that's kind of our first foray into just comparing against other tools. But as I say, we'd love to set up some more test cases in this space, and see how we compare to Plexus and to, for example, Saturn and some of the other tools that might be out there, some work around osmosis, for example, and just understanding where there are any differences or similarities. Obviously, every model doesn't have to give the same output, but I think opening up our models to each other, I mean, as a modeler, it's always a bit nerve-wracking just letting everyone look under the hood, warts and all. But I think the overall quality of the output analysis is then better, and as a community, we can hopefully start to understand the space in a comprehensive way. Are there any questions on this just before I move on to closing out with some of the multinodal work that we're doing? Do you have annual limits? Let's jump in from 20. Yeah, so total installed capacity. So I think this study was a least cost unconstrained, if I remember what we're showing here. So there weren't annual build limits in this specific scenario that we're showing. And in general, we found that the Plexus models were a bit like there were a bit more of these kind of anomalies where you have a big jump in a year compared to the PyPSA model. But we do have scenarios where we then have those smoothed out where you kind of say, okay, well, this is the completely unconstrained, but if you then smooth that out and then have like minimum, I think the way we ultimately implemented it was minimum build constraints that would kind of get you to the same trajectory, but without a lot of these variations. God, sorry, I see we missed your question on dynamics at a node, voltage angle, inertia, etc. Yeah, so I think PyPSA, if you remember back to the first workshop, PyPSA you can think of as a toolbox of different modules, and there's different tools in that toolbox. So the modules that we're looking at right now are very much around capacity expansion and the kind of resource adequacy type modeling. But then you can go, there is a power flow module within PyPSA. And then I'm not so sure about inertia coefficient, for example, but there's kind of a linearized power flow, and there is a non-linear power flow, I believe. I haven't played around with those, but that allows you to look at voltage angles, etc. So you can do a bit more in-depth analysis on the uh, yeah, just in terms of your power flow between different regions. So it has some functionality within the power flow space, but it's not going to be completely the level of detail of some big silent model, for example. Assume pumped hydro sites. So we didn't go into any. So as I say, our model hasn't really actually been building pumped hydro, which we found quite interesting. From what I understand from the CSR model, the 5 gigawatts stems back to modeling around RP 2019, I think. And it was kind of an indication that was provided from DMRE at the time of like the maximum kind of number of potential sites, but I don't think there was any detail around specific sites. The the balance between pumped hydro and battery storage is quite an interesting one. And I think there can be a lot of interesting postgrad studies in this space. But it's definitely linked from what we see in the output to, for example, if you have quite a solar heavy generation mix, then your model is going to favor battery storage over pumped hydro, but potentially wind, that might flip around. And we have seen some kind of, it's not a 100% clear-cut case, like no pump storage and all battery. I think the solution space there is quite flat. So basically, you could go with a mix of the two and kind of get out to a similar answer. Okay, so just kind of to close up, I know it's been a bit of a information dump today, but I think the idea is that, I mean, we're just opening the conversation now, so and we're looking forward to kind of improving the tool as we work with all of you guys who are interested in using it. But we will set up a Discord channel where basically we can ask different questions on the model. And if you get stuck, unfortunately, we don't have a ton of funding at the moment, but we are looking for some more funding that can kind of keep us active and working on the model and providing a bit more support to everyone. So the final kind of the new frontier, I'd say, in terms of modeling, and especially given the focus on the grid at the moment, is now understanding more of multinodal modeling. And this is, I think, where the European PyPSA models have a significant kind of head start on us. So there's a lot of basically the PyPSA Europe and PyPSA Earth models have historically been focused mostly on single year analysis, but very high spatial resolution. Whereas for South Africa, we've always been focused on these kind of transition type questions, and we've had low spatial resolution and higher intertemporal resolution. Now, obviously, in terms of computational limits, you can't do both of these things together necessarily. So you couldn't do like even a 34 node model and like solving in 2-year steps to 2050. It's gonna, unless you have like 256 gigs of RAM or something, you're gonna struggle to solve that. But what we found is we are able to solve a 34 node model, and even the 100, like if you wanted to do something crazy like down to MTS level, you could solve that for a single year in quite a reasonable amount of time. So you might want to say for a snapshot in 2040 or 2050, if you wanted more detail around the location of different generators and some of the inter-region constraints, how that might work out. So that's definitely possible. And then we found that if we use 10 nodes, so at the level of the kind of new sort of demarcation of the ESCOM supply regions, we are able to solve for about 5 years, so 5 intertemporal periods. So, for example, we could go 25, 30, 35, 40, etc. And that can still solve in a reasonable amount of time, kind of less than 2 hours. But if you want to go further than that, the curve in terms of like simulation time just starts increasing exponentially. But we think that the kind of 10 node model is kind of a good starting point and something that we can use in the capacity expansion modeling. And then basically, yeah, that you can do some more detailed spatial modeling, but probably only for a single year. So we presented this last week, but just a quick recap in terms of what is available in the model. So we have GIS data from one of the past GCCAs. I think it was for up till about 2018, and then we have TDP, the actual maps that are produced. Unfortunately, we don't have the new GIS data. So what we've done is we've kind of geo-referenced the images as best we can and basically trace them out in GIS data. So we capture the kind of new 765 corridors and 400 kV investments. From a spatial information point of view, we don't have well, that's kind of in the open data domain at the moment, kind of regional hourly data across all the provinces. But we are kind of working on ESCOM to hopefully publish that to the data portal at some point. So at the moment, the load profile is disaggregated to different regions. You can specify it either based on kind of GBA data or population density. So CSR provide a kind of what they call a mesozone GIS file that essentially splits all these regions into about 50-kilometer area square kilometer cells that fit neatly in different municipal demarcation areas. And that has some data around population and GVA. And then at the moment, like as a kind of very simple first pass, is we just scale the national load data by GVA distribution. So obviously not ideal because like different regions will have different profiles depending on the makeup of load in those regions. And the best thing is to get the actual kind of aggregate data from ESCOM, even if it's at kind of a 10 node region. But possibly some interesting work that could be done. And I mean, the guys from UCT are experts at this compared to us, but some kind of sectoral decomposition and how that might change between regions. There's a whole body of work on kind of load disaggregation and also how that might change over time. But for now, we have a kind of very simplified breakdown of load. But it doesn't help having this kind of very fancy spatially distributed model if we don't have a very good idea of how load is broken down. So I think this is really one of the critical areas that we need as a modeling community as we move into more spatially distributed models. Just a quick recap then on kind of what the network might look like for these higher spatial resolution models. So on the left-hand side, you can see here we would have 10 buses. So there'd be a node at each of these connections in the kind of centroid of the region, and then different connections between different regions. And you can see the kind of level of computational complexity that increases going from 10 to just the 34 nodes. And now essentially the optimizer is figuring out an optimal energy mix at each one of these nodes. You don't provide it all the same generators, so you might not provide it gas generator, for example, somewhere in the northwest. You might have only solar, or you might have only wind in regions, but the computational cost does go up significantly. So that's just what the nodal would look like. So then the question is kind of how do you take this information that you have then on the so we have information from the TDP of different lines between different regions, and how do we start to now estimate what the transfer capacity of energy would be between two adjacent regions? And that's ultimately what feeds into PyPSA at the level of our capacity optimization work that we're doing. And what we do is we start off with, if I go back to the GIS data, basically the GIS data tells us where each line starts and stops, and you map that to a region. So for example, if you have a 765 kV line starting over here at a substation that's in the Western Cape and ending at a substation that's in the hydro cluster, the model then counts that as a line that connects from the Western Cape to hydro cluster. There's now one 765 kV line. It's added, and it does this depending on whatever arbitrary shapes you provided to solve with. So once you've compiled all the different lines between the different regions, then the question is, okay, how do you convert that line into from a voltage level and its length into now kind of a megawatt value that you can use. And for our analysis, what we've been using at the moment, there's different options. So you can do thermal loading. So you can look just at thermal limits. You can also just look at surge impedance loading, for example, between two areas. But what we've done is look at Sinclair curves, where essentially your kind of line loading limit varies by the length of the line. And you have kind of up to about 80 kilometers in line length. The line is limited by its thermal loading, and that's kind of often approximated by in the order of 3 times SIL. And then you have regions where voltage drop and stability limitations. So that we basically have this curve within the model, and it looks at the length of lines and then calculates basically what percentage of SIL is available for each line. So just as kind of like a very simple worked example how we would do this. So if we had two arbitrary regions and we have some kind of substations within each region, any lines that, and basically ultimately we're trying to represent this as a single line between two regions. So any substations that basically are in the same region, those lines are ignored. So we're only interested in lines that are crossing the boundaries. It's not a perfect representation at the moment, because obviously if you have a very short line from here to like your next substation, but you have a long line that's feeding it from within the same region, it's not a perfect approximation, but this is how we started. And you might have different voltage levels if it's 400 kV or 765. So if we just kind of add some random numbers to that, so we could say we've got the crosses, we've got one 400 kV line, we've got two 400 kV lines of 300 kilometers, and we have one 765. We can basically use our Sinclair curve to then calculate basically how many megawatts transfer capacity there could be for each of those lines. And then the question is then how you do the understanding some kind of n-1 approximation across your network. So the way that the standard PyPSA model does these calculations, or the standard PyPSA Europe model, for example, is that it's as far as I understand, it's based purely on thermal limits for all the lines. And they apply a 30% D rating. So they would multiply the thermal ratings by 70%, and that would be the kind of approximation of transfer capacities between different regions. You can also kind of have a more conservative, if you were to apply 50%, for example, then that kind of is an approach that we use if we only have like, there might, especially if you're doing higher spatial resolution models, so say like the 34 node model, etc. There are some cases where you might only have one line between two regions. And in that case, we've been applying a D rating. But for example, for the 10 node model, we've been knocking out, so just remove the largest line between two regions as a different approach to n-1. So you can see then how the kind of calculated transfer capacities would be then between different regions. So if we put this together, then how these might change over time. So one thing that we don't have complete, well, that's not represented in here is if some of the lines on each end are doing bar support, for example, and that would reduce some of the transfer capacity in megawatts that can happen. But then also some of them might be compensated, which then raises it again. So those two factors are kind of canceling each other out, but it might swing it one way or another. So at the moment, these are kind of our calculations. And if we take the existing grid, we kind of have in the order of 2.7 gigs of transfer capacity, for example, between the Western Cape and the Hydro cluster. And then as the TDP unfolds and we have another 765 connection that comes in, we can see that the transfer capacity between these regions is increasing, but still limits really in terms of how much can be moved through the central corridor. And then as that expands even further, we can see that the strengthening of all three corridors that we land up with this kind of spread of between about 4 and 7 gigs across the corridors. Obviously, a lot of kind of very detailed grid information that kind of hasn't gone into this. So this is definitely something that might need to be refined a bit over time. But hopefully it's a first step in terms of how we can do some multinodal analysis. In terms of how this is actually represented within PyPSA, we've used kind of a derating model. So what we do is we take the line capacity at its absolute maximum. So if it was 2035 or 2040, and we make our base network has that maximum capacity, and then we derate that line. So as far as PyPSA is concerned, it would be a 7.3 gig connection between these two regions, but then that's derated down to 4.8 gigs in earlier years. It is possible also to assume some losses within the network. So we are not modeling these inter-region transfer capacities as passive flows. So we're not modeling them using the lines component and basically taking into account impedance between different regions. At the moment, it's kind of a DC transport. It's kind of like an HVDC transfer type model. But it is possible to do more detailed power flow studies once you've kind of done your capacity optimization. And we do use links then, and it can either be a lossless link. So if you assume a lossless link, then you don't have to, you can have a single link between different regions. But if you want to apply some kind of losses, so relative to distance, then actually what you need to do is represent it as two one-directional links, because a link in PyPSA can't take an efficiency loss and be bidirectional. So you have to have losses going one way with a one-way link, and then losses going the other way. You can, if you want to do an optimal capacity, Bruno, you can make lines extendable. So this doesn't work. I haven't figured out a smart way to do this yet in if you have multiple years that you're trying to solve, because it gets a bit messy. You're going to have basically each line between each region getting optimized each year. And I think the tractability of the model, if you have multiple years, is going to get out of hand a bit quickly. But if you're doing a single year, it's very easy to then, if you wanted to co-optimize the transmission capacity and the generation capacity and see where you are making investments in different lines, that's definitely possible. I think where we're leaning towards at the moment is we know kind of roughly what the main corridors that we'd want to strengthen are. And basically exogenously applying that, you can manually add lines between different regions and then test how that might influence your build out. So at least in terms of the capacity expansion planning over time, that's where the model's sitting. But maybe there's a way to do the co-optimization over the horizon as well. My gut feeling is that it's just going to be quite heavy computationally, and it's going to conceptually strengthen the lines that kind of some good judgment would say, okay, these are clear bottlenecks in the network. So it's quite easy to then manually address those bottlenecks. Okay, just before we wrap up, I don't know, are there any questions or comments on the multinodal stuff? So we haven't published this just yet, but we're working on kind of hopefully getting this model out soon. Etienne, one of the devices going ahead and should be operational in 2025. Why is ESCOM doing devices? Yeah, so I mean, I think Etienne, like I said, the case of it all storage as batteries and none as pumped hydro is something that you actually have. This is one of the challenges of looking and using an optimizer, is it provides you a single point on the space, but that space, that solution space might be completely flat. And I think what you'd likely see is that you could have differing penetrations of pumped storage and battery storage and get up to a similar optimal energy mix. So I think it's definitely something that you have to use these capacity expansion models with caution, and it's not be completely in model land. It's not saying that there isn't a role for pumped hydro. I think one of the challenges that pumped hydro, I'd say, is facing is the pumped hydro is great from a dispatch point of view if you have long duration storage and you can kind of capture especially some moving wind patterns, for example, weather patterns, and store it for the shift from, say, more than just one day to the next. But part of the problem is that to actually charge the storage, your long duration storage bites you on the charging side because you can only charge it at a very low rate. Whereas often you're getting these spikes in power for short periods of time that are happening often, and each time the pump storage can only go to, say, one. If it's a 1 gig unit, but it has 20 gigawatt hours of storage, you can only charge at 1 gig each time. Whereas you're having battery storage coming in with 4 hours, so a 1 gig battery or so basically like a 5 gig battery would have the same gigawatt hours. So you can grab that extra energy. yeah, in terms of what's happening on the actual projects, I don't know where Tabats is currently standing, but um, obviously the kind of South Africa's history with large mega projects can be challenging. Um, but yeah, so I mean, these are the kind of things that you can test in the model yourself. If you make an investment in a commercial solver, you can start to test even at a regional level. Does it make sense to have more pumped hydro? What is the cost premium? Uh, what if we assume different costs for pumped hydro? What if you look at it at different scales? These are all kind of studies that you can do yourself in these kind of models.
Thanks. If I can just comment on that. I think
Sure.
there's an important role for batteries and pump storage. They each have their role. Batteries are perfect for ancillary services and for intraday type storage. And what's nice with batteries is you can put them where you want them. You're free to put them where on the transmission grid, you've got constraints. And so you can unblock the transmission grid. But for long-term storage, such as monthly or interseasonal, batteries can't do that. Or batteries aren't efficient, and pump storage is far better. Now, pump storage, its round-trip efficiency is less than batteries. So that's a downside for pump storage. But and because you can't choose where you put your pump storage, it's less suitable for ancillary services. Now, on your comment that pump storage, you need a bigger amount of kilowatts to pump up to the top reservoir. True, I agree with that. But then what you do is you charge the batteries for balancing the grid when you've suddenly got wind. And then when those batteries are full, you use those batteries to fill up your pump storage. So I don't see that as a constraint. What I do believe is pump storage would be, okay, first of all, they're large, they're expensive, and they take a long time to build. And that's the big downside of pump storage. While you can do a battery, you can import it from South Korea, and you have a total project timeline of 18 months. And you don't have much risk in that the batteries are made in a warehouse. And so you can actually get a fixed delivery time. With pump storage, it's more tricky in that you don't know what geological faults you're going to get until you start digging. There will be some things you didn't know were there. And I mean, you see Snowy Mountain, and there's a whole host of projects which have failed. And like you say, they're mega projects. So it's just a recipe for corruption and state capture and all the other bad stuff. But long term, we need long-term storage. And there's a place for batteries and pump storage. Now, because pump storage takes so long to build, if we need one in 10 years' time, we better start building now. Like in Guyana, took 12 years to build. There were issues with it in that there were some deaths. So the construction stopped for a while. But they're long projects. They're risky. You don't know the capex when you take FID. And yeah. And the advantage with pump storage is you build it with local labor, and so it creates more jobs in the country, as opposed to buying batteries from South Korea. And all you really do here is put the Lego sets together, and we don't create jobs. Sorry, yeah, I'm ranting here, but yeah, that's my views.
I mean, yeah, so obviously, I mean, at the moment we can get into long debates about the energy mix and the outcomes of these models. I think we're gonna just here we're very focused on like this is the tool. But as I say, yeah, because the current model as it is not including a huge expansion of pumped storage. That's definitely something that's on our expansion horizon. I mean, I think to investigate further, I mean, what we're seeing, if you look at the kind of dispatch of the model, is that really on the one side, you have your batteries that are doing this intraday cycling, but your pump storage, anything, as I see Bruno saying in the comments, it's not like a seasonal type storage, and really we are building significant capacity of flexible OCGT or CCGT that are handling those periods when there's kind of what the Germans say, the Dunkelflaut, and there's low wind and solar resource. So it's kind of balancing that medium to basically when there isn't enough generation, the flexible generation is running, and all the short-term dispatches is being handled by battery storage. But definitely something that you can these are all scenarios that you can test in these kind of models. You can force different levels of pump storage in and then look at what that does to your objective function. You can look at how the system dynamics change. Who knows, once we move away from the single node model to the multi-node model, there might be more localized benefits of doing different storage in different regions. So tons of interesting stuff to explore. And at the moment, this is kind of just a framework where you can start to test these kind of hypotheses. But definitely, we're very wary of saying, like, this is the plan, this is exactly what the optimizer spits out. I think where everything is moving is to running ranges of simulations and varying parameters and actually looking at that cost spread. And you might find that you can have a completely different looking power system for within a couple points of a percent of the exact point that your optimizer found. And then it becomes questions of some of these other questions of localization potential, etc. What are some of the added benefits? Okay. Is there anyone else? It'd be interesting. I don't know if anyone's brave enough to jump out. Oh, sorry, Bruno. Reserves in a region. Yeah, so it's not coded in at the moment. If you wanted to, so you say, for example, I have a certain amount of spinning reserve based on dispatchable capacity in a region. That's not coded in at the moment, but it's definitely something that's quite easy to do with the custom constraints. So with LinoPy, you can basically pull in any kind of variable and you can group different technologies, and you can say at each bus, there must be a certain amount of reserve capacity. I must say we don't include operating reserves at the moment in the capacity expansion model. We've kind of subsumed that into the planned reserve margin, which is typically on the higher side of that reserve. But in the dispatch model, then there's more detail around spinning and non-spinning reserves. And for example, I mean, there's some interesting work that you can do around kind of like minimum levels of inertia in different regions. Those kind of things you can start to play with custom constraints. So I don't know if anyone's brave enough to give some feedback if you managed to play around a little bit with PyPSA, if you found anything useful from the series of workshops. We hope that this is kind of enough to just get everyone started. But part of the way that these open source models work is it's really about collaboration and having lots of people using the models. So I think what we'll probably find is that we've tailored this model very much to kind of how we like to use it, and developing a lot of the code. It's like it works for us, but it might not be completely intuitive for someone else coming in to use it. So then that's definitely areas where we can kind of partner and hopefully in kind of a year or two, and we can get some more postgrads working in this space, that we can kind of refine the model and kind of squash any bugs and kind of shore up some of the technical input assumptions. I think that would be great. One of the questions we've tussled with a little bit is like, do we need a PyPSA-RSA model? Should we not just fall back to PyPSA-Earth, for example? And I think what we're keeping an eye on is when the kind of perfect foresight and myopic expansion paths that are in PyPSA Europe start to filter into PyPSA Earth. And then it's definitely something that we could consider basically merging in some of the more detailed parts of this model that we see into PyPSA Earth for the South African region. But then that's something that we'll have to make a call on as we go along. But there's quite a lot of very South African specific type info in this model, at least, which isn't currently in PyPSA Earth. But it is useful to kind of keep benchmarking against other PyPSA models to see kind of how they, what those outcomes look like. Yeah. So I mean, I think the way the model is set up now, it's quite easy to expand the geographical footprint. So everything is kind of generic. So if you wanted to have a SAP model, for example, the only thing that you need to change is get a bit more detail for other countries, and then upgrade your GIS information, and then you're pretty much ready to run. But definitely getting the country specific data is always the challenge. And yeah, our kind of modeling of hydro at the moment is quite simplistic. We basically are just taking the hydro import profiles that are from the Eskom data portal, and just kind of running our hydro in that same sense. But there's definitely some work around, you can use AtLight to calculate runoff, just like so you can get more renewable resource profiles similar to wind and PV, rather than just relying on the Eskom data. Okay, I see we are 5 minutes over time. What was the simple snake make? Got something. Sorry, Bruno, maybe you just want to ask your question directly.
You started your lecture with a simple snake make, which I tried to type in on my side. But I think I must have missed a step, because when I put it in, what I remember, I'm getting missing optional dependency OpenPYX1.
Okay, so that sounds like there's maybe a Python library that's missing. So
I need to install PYX1 or XL or
yeah. So basically, I mean, this is great when something like this pops up. If you can either drop a message on Discord, or on the actual, just raise an issue on GitHub. And for example, then we can just quickly make sure that OpenPyXL is in the install environment, because it's clearly not picking it up when it's installing. So the link here, so we have a PyPSA-RSA Discord. We have had a few initial conversations with the group at Stellenbosch, but if you click on this link and you register for Discord, then that's kind of a great way for anyone who has specific questions. The biggest learning hurdle is getting everything installed and working. So don't give up if it's a bit frustrating at the beginning. But once you've got all your Python environments and everything going, then it definitely gets easier and quicker. So we can't kind of spend a huge amount of time each day helping people install Python environments, but if you get really stuck, then you can pop a question and we can see. As I said, the other thing we're gonna have to do is just update the scripts to use the new version of Pandas grouping for weeks. So if you run the full workflow on your side at the moment, it might throw an error around that. And it's just because I'm still using an older version of Pandas, so it hasn't flagged that error yet. Etienne, final question. All the assumptions used are in the different spreadsheets. So just open it again here. If we go to example for extendable technologies and you go to parameters, and then you can filter here via whichever scenarios. If you want the default RP and you want pump storage, you can get some of the info that's been applied. So that's on the RP. We have no idea why they had a variable O&M charge of 544 on the pump storage. But for ours, we didn't apply that. So
thanks for that. But what about Meridian and these other people that also do modeling? What do they assume?
So I mean, you can ask Bruno's on the call. You can ask them what capital costs they've assumed on pump storage. We use the RP capex value when you basically look at the capex cost of Angular versus installed capacity. It comes out at roughly this number. So I think that's maybe how ESCOM and DMRE came up with that number. But it seemed reasonable to us. So if we didn't have a good reason to deviate from an RP number, we didn't. But we didn't include the 544 Rand per megawatt hour on the variable charge. So that we excluded. So you're looking at 31,000 kilowatts installed.
I think one of the key parameters is how long does it take to build? Because that's what I think kills pump storage in quite a few models.
Sorry, I'm afraid you're breaking up a bit.
Sorry. What's quite important is also how long does it take to build the pump storage? Because I mean, if it takes 10 years or 5 years, your economics will be very different.
Yeah, so the costs that you provide to PyPSA in terms of your capital cost it's not an overnight cost, so it does include cost of financing as well.
I understand that, but here, am I right to say that you've assumed a 5-year construction time? Or 6 years,
Yeah.
sorry, 6 years.
We assumed whatever was in the RP for pump storage.
Okay. Thanks.
Okay. I don't know if anyone has any final comments before we close. Be great if anyone has any feedback, and hopefully we can see you guys active in the model, finding things to refine, and we can definitely improve it by getting this model off just Meridian working on it. Okay. If no one has any burning comments, we can call it a day there. So thanks very much. We'll again, these slides will be available on our website, and we'll have the videos available there as well. And depending on the work I have next week, I'll try to get the push to GitHub by the end of next week with the updates, and then the model should definitely run with everyone's new environment. Thanks, everyone. Cheers, cheers.